Welcome back to our stochastic processes. We are in the last video of the topic of Markov processes, and we learned about time homogeneous Markov processes last time, where we introduced the operator semigroups and their generators. At the end of the last video, we saw that the generator gives rise to a lot of martingales, and the only task of this video now is to produce examples for this. So let's start. So we already have some examples of Markov processes, in particular the Poisson point process and the Brownian motion. But let's see what we can come up with today. Let me recall a bit from last video. The main things that we are going to need today is time homogeneous Markov process, its operator semigroup, and let me recall T f of x was defined as the expectation when starting in x of f of xt. That operator semigroup here has a generator, which was defined by this limit. And we saw at the end of the last video that if gf exists, so of course limits don't have to exist, but if they exist, then this process here is a martingale for all suitable f. Let's start very simple. A particular Markov process is a deterministic one which solves this ODE for some nice function g. I mean, it's not stochastic, but of course it's a Markov process because the future, so how the path continues, only depends on the current thing, so it does not depend on the past. And that's exactly what is written down here as an ODE, an ordinary differential equation. And that's also time homogeneous, because the g does not depend on t explicitly. And so this time homogeneous Markov process has to have a generator. The only thing that I don't have to write today, as on this slide at least, is an expectation, because there is no randomness, so I don't need expectations, such that the generator is only here the time derivative at t equals 0. And what is the time derivative of this thing here? We know the time derivative of x, but we here need it of f of x. So that's the usual chain rule or so. I have to compute the derivative df by dxi times dxi by dt. dxi by dt is given by the ith coordinate of g. And I can write it differently. Here's the gradient of f at g of x times g of x. And this here is a scalar product. So that's now the generator of this Markov process here, as an example. Here's another example. We already computed last time. Where was it? Here. The generator of the Poisson point process is given by a rate times f of the new state minus f of the old state. For example, if you're using f equals the identity, then this here is just 1. So that's this difference here, that's 1. So xt minus lambda t must be a martingale. And probably we already computed this. Let me also mention that I'm doing something which is slightly wrong here. When you pay attention, so at the last time and in the last slide there were these martingales. f here was in the domain, and most often functions in this domain here must be bounded, because then there is no issue with integrability in all the expectations that we're writing down. But on the new slide, on the Poisson point process, I want to use f of x equals x, and that's not bounded because x can run through the whole natural numbers. But if somehow I can guarantee integrability, that's not a problem, and I'm just doing this here in order to compute some martingales. And I had here xt minus lambda t is a martingale. I can also use the same thing by saying f of x is x squared. So I'm getting this here before the integral. And I have to apply this to a generator applied to f. And there's a bracket missing here. Generator, so f of the new state is x plus 1 squared minus x squared. Okay, this difference is 2x plus 1. And that's therefore also a martingale. Maybe you remember that we had that on some exercise sheet. Another example is Brownian motion. Here we computed last time. The generator of Brownian motion is a 1/2 f double prime. So when we are taking the f of x equals the identity, the generator is 0, which means xt minus, well, integral over the generator, that's 0, xt is a martingale by itself. If I'm using the function f of x equals x squared, then 1/2 the second derivative is 1. So this here times that 1/2, that's 1. That means I'm integrating over 1 from 0 to t, which is t, and xt squared here, so I have this here. That's also a martingale, and we already computed this. A third martingale, therefore I have to skip back to the last video. Not only f minus integral over the generator is a martingale, but also function times e to the minus integral from 0 to t, gf divided by f is a martingale. Okay, f should not be 0 along the path, otherwise the denominator here, just wouldn't work. But then this here is a martingale. And as the f of x here, let's consider f of x equals e to the power of mu x. So if f of x is equal to e to the mu x, then gf of x, well, it's 1/2 times the second derivative, and this is mu 1/2 mu squared e to the mu x. And what I have to do here is to compute f of x times e to the minus, and I have to produce here gf divided by f. Well, gf divided by f, that's 1/2 mu squared. So the thing here is 1/2 mu squared, and that's in the integral here. So this one here is also a martingale. As we now can easily compute using the generator, and we do not need any conditional expectations for this. Another example are Markov jump processes. We are saying a jump when I'm currently at state small x occurs at some exponentially distributed time. according to some kernel mu. And we will write lambda x dy equals lambda of dx times mu of x comma dy. So lambda x dy is the rate by which the process jumps from x to y. So how can we compute the generator? Then the calculation is pretty similar to what we already had at the Poisson point process. Because as I mentioned here, what's written here, rate times f of new state minus f of old state. It turns out that's a general thing. Okay, I'm integrating or summing over all possible places where I jump to. Lambda of x times mu x dy is the rate by which I jump from x to y, times f of y minus f of x, so f of new state minus f of the old state. And the reason why that's the case is in this limit here. Okay, if there was no jump at all between time x and time 0 and time t, then the numerator is just 0. But if there is one, so there can be one jump, and there can be more than one jump, but more than one jump in a small time of amount t has probability something like t squared, divided by t, that gives a t, and limit to t to 0 gives nothing. So the only contribution to the generator are single jumps between time 0 and time t. And when you take them into account, you exactly get to the form of this generator here. Okay, and then we had also Feller semigroups, or yeah, what must be the case here? So lambda must be continuous. And bounded, of course. Yeah. So, yeah, because for Feller semigroup, the operator semigroup has to be continuous in the initial distribution. And if lambda is not continuous in this x here, that will just not be the case. Okay, for such Markov jump processes, there is something physicists like to call the master equation. The master equation is the following. Let's read it also from left to right. So I want to compute something like the probability that xt is x. So what's the probability that my process at state t is in state x? And there is a differential equation attached to this. And how can it be that xt equals x? Well, it is in z shortly before, but it jumps at rate lambda zx from z to x. And the other thing which changes this probability here is that if I am at x currently, but I'm jumping away from it, so minus lambda x z, p of x equals x. And as you see, I have these probabilities here, here, and here. They are unknown, but this here is a linear system of ordinary differential equations. And when you solve this, you compute the distribution of your process. So why does this hold here? So what you have to do is you use f of y equals this function here in your usual generator calculation. And observe this here, that's true always. expectation of gf of xt. You plug it into your generator. You're using the Markov property. On condition on xt equals z. And then you can evaluate here one sum here and here the other sum. And you put everything together and you end up with this master equation, which very often appears in the physicist literature. So you now know what that means. Here are even more examples, which are branching processes. That's a special form of such a Markov jump process. So I think we are starting here with one individual, say. Every individual dies at rate 1, and every individual is replaced by some independent random variable z, which is distributed according to some offspring distribution. Well, that's a special case. So what's the probability to jump from x to x plus n? Well, this is x times mu of n. So that one individual here dies. So that minus 1 here is it dies and is replaced by n other individuals. So minus 1 plus n, that's the new state, minus f of x. And this here is f of the new state minus f of the old state. So it's again the rate by which something occurs times f of the new state minus f of the old state. And that's a nice form for the following reason. I can use this function here, f of x equals r to the power of x for an arbitrary r. And then, well, f of x minus 1 plus n. So it's something times r to the x minus 1. And either r to the power of n in the first place here. And r to the x minus 1 times r is r to the x, which is f itself here. I call the moment generating function, so mu of n, gr of mu. I'm calling this here the moment generating function, and that is here the g mu of r. And this is exactly what's written down here. And for the later part, well, mu of n I can sum over, that's 1 times r. And this is actually the same. So in particular, this x times r to the x minus 1, you could also see as the derivative of f of r of x according to r. So that's interesting, because I can then write this function here solves the equation. Well, this one here. G f r of x is a time derivative. That's the time derivative, which exactly looks like this for this function here. And g mu of r minus r, well, that was from the generated term here. This here is from the left-hand side of the above calculation. And I concluded that this here holds. Okay, there are some boundary conditions for this function u. And this is nice because now we have a partial differential equation. It connects the time derivative here with the r derivative here. And when we solve this, we also completely solved this branching process in continuous time. Let's get even more special. Mu equals delta 2. So which means an individual dies and it's replaced by 2 new ones, always. Or put differently, there's one additional thing here. So one additional thing. So first of all, g mu of r is r square. As you can see, because there's only a case where you have two offspring, so the expectation of z of r to the power of x is r square, and you're facing this differential equation. So what was here? G mu of r minus r. G mu of r minus r. That's correct, because for g mu of r you have the r square, which is this thing here, minus r. So I have to solve this. And I'll just give you the solution, which is this one here. And with some experience, you can see that the right-hand side is the generating function of a geometric distribution with parameter e to the minus t. And UTR is by definition the moment generating function of my random variable xt. And it has this form, which means that xt is geometrically distributed with parameter e to the minus t. You can also solve that differently. You can also solve the full master equation in order to see that xt has this geometric distribution, also solves this master equation. Okay, two more examples. Again, for a branching process, the probability of extinction. So t is the first time xt equals 0, is the extinction time. And we want to compute the probability that this is a finite time. So if the process eventually starts, the process eventually dies. So first of all, if you start in x, then since everything is independent, the probability that the process dies when you start in x is the same as the probability dies when you start in 1, but x times, so to the power of x. And I'm calling r the probability when you start in 1 that the process goes extinct. Well, and this equation is a bit vague, but let me explain it. So what is r? R is this probability. How can this be computed? So there's a chance of roughly 1 minus h that that nothing happened. And then of course, in this case, the extinction probability just stays the same. In the other case, it jumped from 1 to 1 plus n, or from 1 to n, with the rate mu of n. Then I have n, and the probability that it goes extinct is r to the n. Yes, because that is the same as when you start with 1, x times, n times here, plus O of h. So if h goes to 0, this one goes away. And therefore, well, this O arc is against this r. Then we have only h's. And for n equals 0, I have a 1 here. Yeah. So and this goes h times r, yeah. Here I have h times r, and here I have h times g mu of r. So I can divide by h, and this is the equation that I get for the extinction probability. So I have to solve this. Apparently r must be less or equal than 1. And you can go through the calculations. So that's essentially not hard now, because you just have r and you have g mu of r. And for g mu of r, I get a form. And I can solve this here for r. And that must be the extinction probability. But let me mention, if r equals 1, so r equals 1 is always a solution here, as you can see. But if r is not 1, it's maybe different. So when you go through the calculations, when you, for example, have binary branching, so you have an atom at 0 and an atom at 2, the only solution to this equation here is this, and that must be the extinction probability. That's one thing here. And the other thing here are hitting times. So again, we have a general jump process. And t is the hitting time of some state space. And I want to compute the expected hitting time of something. And how does this work? So u of x is the expected hitting time when I start in 0. But of course, if I'm starting in E prime anyway, then u of x must be 0. That's part of a starting condition now. And I'm writing lambda of x as the sum of all lambda xy. So lambda x is the rate by which I jump out of x. So now we can make the following equation. So the expectation of t, either nothing happens in the first time h. If nothing happens, I have the waiting time t plus h. And if something happens, I again have here the waiting time when starting from y. So that's this thing here. Times this probability. So yes, so I have this thing here, and let me first write that down from here. So I have the expectation of t times 1 is this. The h terms I have to collect, and h squared terms I do not collect because they will vanish anyway. So I collect them here in the h squared term. And I have h times 1, and I subtract h times lambda x times the expected extinction time that I want to have. And for the other term, well, I can compute just with lambda x comma y, because that's the probability that I will be in y when I start in x. But this here comes also with an h, by the way, because only then, when you have a jump, which occurs with probability lambda, which probability h times lambda x of y, sum over all y, then I have this here. So I have this. Now I can collect. I can have the expectation here, O of h squared, and all the rest. I mean, this here is minus lambda x times this thing, plus all these things here, and they are rate times new function minus old function. So it's exactly the generator which I have here applied to this function that I want to compute. So okay, these two go away anyway, in order for this to hold. Minus 1 must be equal to the generator applied to this thing here. So I have this when the boundary conditions are u of x equals 0 for x in E prime, because there we said that they don't have to hit anything because it's already there, so there's no waiting time. So you can solve these equations and you computed the expected hitting time of something. Last example, birth-death processes, which are again special Markov jump processes. They're special because if they're in x, they only jump up 1 or jump down 1 at rate lambda of x and mu of x. Or let me write it as I have here on the slide, which is from n to lambda of n, mu of n, for upwards and downwards jumps. So these are the rates. I have this generator, rate, times f of new state minus f of old state, f of new state, f of old state. So it's always the same. And I want to compute the expected hitting time of 0. That's my u of n, and I'm claiming, okay, u0 of 0 is 0, and u of n is this formula here, I claim. So I have the mu's here, the pi's here, they are also only dependent on lambdas and mu's, so that's okay. And I'm claiming here that this u here gives my expected extinction time. And what do I have to compute? I have to compute that g applied to this function here is minus 1, and it is really minus 1. I mean, you can convince yourself. So what you have to do, lambda n, okay, that's written from here. F of n plus 1 minus f of n, that's the sum over n terms, and the difference between the n plus first and the nth term here is just the n plus first term here. So 1 divided by mu n plus 1, pi n plus 1, yeah, and like this. And I have to also deal with mu n, it's here. F of n minus 1 minus f of n. There I of course keep the nth term here, but with a minus, so 1 over like exactly this. And now, so what was pi n? Yeah, I have pi n plus 1 here. I'm multiplying with mu n plus 1, and I'm dividing by lambda n, and the result is pi n. So this here is the first term, and for the second, well, the mu n here vanishes, so I have pi n like this here. So I'm subtracting these two things. Apparently only the nth term stays here, so pi n over pi n, and this is stays here. It stays here, and additionally, so I'm ending up with having minus 1. And that was it for the Markov processes. And next time we are going to start to deal with Brownian motion and its properties. See you then.